Hello everyone. In this video, I'll talk about what scan chains are and how they are used to detect faults in a chip after fabrication. First, let's define what a scan chain is. A scan chain is a series of scan flip-flops interconnected in a sequential circuit to enable fault detection in a manufactured chip. Here is a very high-level diagram of a scan chain in a design, where the scan flip-flops, also called scan cells, form a chain and the input data is shifted through the chain over successive clock cycles. Before we delve further into scan chain design and examine how scan chains are used for fault detection, let's first understand the fundamental building block of a scan chain, that is, the scan flip-flop or the scan cell. There are several different implementations of a scan cell. One of the most popular and widely used implementation is Mux-D scan cell. Let's take a closer look at the internal design of a Mux-D scan cell. A Mux-D scan cell is an extension of a regular D flip-flop. The circuit diagram of a Mux-D scan cell is shown here. It contains an additional 2:1 multiplexer and few extra pins. The data pin D, the clock pin CLK, and the output pin Q are the same as those of the regular flip-flop. The extra pins are SI, scan input, and SE, scan enable. The multiplexer selects between D input and the SI input based on the value of scan enable. When scan enable is 0, the scan cell operates in normal functional mode. The D to Q path is active and the value present at D pin is captured and it appears at Q output on the active edge of the clock. In this mode, the scan cell or the flip-flop behaves like a regular D flip-flop. When scan enable is 1, the flip-flop operates in scan mode. The value present at the scan input SI is captured and propagated to output Q on the active edge of the clock. Note that in this scan cell, the Q pin also acts as SO or the scan output pin. From hardware perspective, the scan cell is slightly costly compared to the regular D flip-flop due to the added multiplexer and the control logic. These cells are provided as a part of the standard cell libraries alongside of the regular flip-flops, making them readily available for designing scan chains during the ASIC design flow. Now that we understand what a scan cell is, let's discuss how a scan chain is formed in a design using these scan cells. Suppose we have a design with 3 regular D flip-flops with some combinational logic in between these flops, and we want to modify this circuit to enable testing of this circuit after the chip is manufactured. The modified circuit looks like this. Let's go through the design updates that are made here compared to the original design. The first modification is to replace all regular D flip-flops with the Mux-D scan cells. For the pin connection, the D, Q, and CLK pin connections of the scan cell remain unchanged. They are same as the regular D flip-flop. Now let's see the connections for the new pins. The SI input of the first scan cell is connected to the chip level scan input port. The Q output of the first scan cell is connected to the SI input of the second scan cell. Similarly, the Q output of the second scan cell is connected to the SI input of the third scan cell. In this way, the scan cells are connected back to back to form a scan chain. Finally, the Q output of the last scan cell in the chain is connected to the chip level scan output port SO. After forming the scan chain, we see that there is a direct path from the scan input port SI to the scan output port SO through the scan cells 1, 2, and 3. This path behaves like a chain of shift registers. This shift register behavior is active when the scan enable input SE of the scan cells is set to 1. To achieve this, the scan enable input of all the scan cells are tied together and connected to the chip level scan enable port. When the scan enable port SE is 1, any data applied at SI is captured by the scan cells in successive clock cycles and shifted through the chain from SI to SO. In this example, the scan chain contains 3 scan cells, and the data applied at SI port can be shifted into the chain in 3 clock cycles. Suppose after reset, the 3 scan cells contain 000, and we want to load a value 101. To do this, we apply 101 serially at SI port and set scan enable SE as 1 and toggle the clock. After 3 clock cycles, the desired values are loaded into the scan cells, which are then available at the Q pin of the scan cells. In similar fashion, the scan chain of n scan cells can be formed. In this case, the scan input applied at SI port can be fully shifted into the chain in n clock cycles. After all the design updates done in the original design for scan chain insertion, let's look at the modified design closely. In the modified design after the scan insertion, the Q pin of the scan flip-flop can be treated as pseudo-primary input. This is because if we want to force any value at Q pin, we can do so by applying the desired value at the scan input port SI and setting scan enable SE to 1, and then by shifting the value through the scan chain. As a result, the Q pin is loaded with either logic 0 or logic 1, and this can be used to drive the downstream combinational logic. Thus, we see after the scan insertion, the Q pin behaves like a pseudo-primary input. Similarly, any value present at the D pin of the scan cell can be shifted out through the scan output port in linear number of clock cycles. This makes D pin an observation point, since whatever value appears at D can be propagated to SO output. Hence, after scan insertion, the D pin behaves like a pseudo-primary output. To summarize the key characteristics of the scan chains, any desired value can be applied to the Q pins, which act as pseudo-primary input, and any value present at D pin can be observed as they act as pseudo-primary outputs. As a result, scan cell insertion effectively transforms the testing of a design with sequential circuits into the testing of only the combinational logic. This means that engineers and testers need to focus primarily on testing the combinational logic blocks that lie between the scan cells. Since the combinational logic is either driven by primary input ports, shown here as A1, B1, A2, B2, and A3, B3, or the Q outputs of the scan cell, which serve as pseudo-primary inputs, by setting scan enable to 1, designers can fully control the pseudo-primary inputs, and by shifting the data through SO, they can observe the pseudo-primary outputs. Thus, we see that by implementing scan chains in a design, the internal nodes of the circuit become highly controllable and observable using limited number of test patterns. This greatly improves the testability and makes fault detection in the manufactured chip much easier. This is all for this video. Hope this is helpful.